Okay, so next thing that we're talking about is called chemical equilibrium. Okay, so basically anytime there's a reaction.
Dr. Henry,
What? Not
we're
working?
seeing
Oh, double.
everything.
Okay, good.
I don't want to get yelled at. I just want to tell you.
Okay, I'm happy. Glad you told me. Okay, that is really weird. How about now?
We see the
Single.
You see the single?
Yeah.
Okay, good. So you're not seeing the answers to the test score. Okay, so basically when there's chemical reactions, a lot of reactions they don't react completely. So one of the things that you guys kind of learned when you were probably in 2A, we had talked about weak acids, things like that, where they partially dissociate. You don't get a complete dissociation in the case of a weak acid. You guys remember that?
Vaguely, but yeah.
I remember you saying strong acids completely dissociate because they're strong and independent.
That's right. Okay. So, well, in reality, a lot of chemical reactions don't go completely. So not all of them will completely dissociate, or not all of them will completely react. And so what you get is something what we call equilibrium. And that's usually dictated by a double arrow, or you'll see it written, the double arrow here, or you'll often see it written like this, where you have an arrow, partial arrow going both ways. Okay, so what that basically means is that the reaction is reversible, right? Meaning that we can go from, let's say if we're talking about the dissociation of water into its ions, I mean into its elements. Okay, can you guys see my purple?
Yeah, it's showing up.
Okay.
Yeah.
So in this case, water dissociating into its elements is a reversible reaction. Usually you'll have, let's see, there's going to be a competition that's going to be occurring between the forward reaction, which meaning going from right to left, from left to right, and then, or the reverse reaction, which is going the opposite direction. So in this case, the forward reaction will be going water being decomposed into its elements. The reverse reaction will be the elements making up water, okay? So there's a competition that's occurring between those two. And there's going to be a point where these rates reach what we call equilibrium, or a dynamic chemical equilibrium. And then that's basically when you get a overall no net change between the reactant, the concentration of the reactants, and the concentration of the products. Okay. So you got to think of it as it's always happening, because basically what happens is that when you put, let's say we're putting water in the system where there's no elements in there, as soon as that water hits the system, it's going to try to reach that point of equilibrium. Okay. And so it'll start at a point and then it'll shift proportionally to try to get to the point where you have no net change happening between the water and the ions that are being generated. I mean, not the ions, the elements that are being generated. Does that make sense? You guys see what I'm saying?
Yeah.
Mhm.
So let me show you what it means mathematically, right? Because then you start seeing the mathematical connotation, it'll start making a little more sense. Okay. Okay, so here's our hypothetical equation. So we have Ma M is our coefficient, A is our compound or element, plus NB yields XC plus YD. Okay, so the first thing that we would define is called the quotient. The quotient is basically, it's going to be that value at any given point or any given position during equilibrium. And so the way that we define that, the quotient, it'll just be QC is going to be equal to the products, and it'll be the products, the concentration of the products to the power of that coefficient times the other product to the power of that coefficient divided by the reactants. So it's always going to be products over reactants, and you're going to use their coefficients as the exponent for the concentration. Okay, and then that's going to equal our quotient. Okay, for the reaction at that given point. Okay, now at equilibrium, our quotient is going to be equal. Our quotient is going to be equal to our equilibrium constant. Okay, and that's going to be our Kc. If the quotient is greater, than the equilibrium constant, then your products, you have so if let me think about this. So if Q is greater than the equilibrium system, then the reactant is going to want to form you're going to want to form the reactants. Okay, and so you're going to be pushing the equilibrium going the other way, right? So, and if the quotient is less than the equilibrium constant, the reaction is going to be going towards the products because it wants to try to reach equilibrium. So it's going to be going the opposite direction. So it's going to go towards the right. Does that make sense?
Yeah.
Okay.
And this K is not the same K from the rate law, right?
That's right. That's why the rate law is a lowercase k typically. This K is typically an uppercase K.
So how would we know if QC, like how would we know it's relative to K? Would we just be given K?
A lot of times you're given the equilibrium constant or the equilibrium value, or you'll be calculating the equilibrium value.
Okay.
Okay. Now, this also works with pressures. So if you have partial pressures, because in a system, you're going to have partial pressures associated with the system. So we're often talking about a system. So all of the things that are in the system that have gases that are going to be associated with it are going to provide a partial pressure associated with that. So you can use that partial pressure to sit there and calculate the equilibrium constant because PV equals nRT under the ideal gas law. And because of that, we can sit there and say that the number of moles can be proportional to the pressure that's associated under those circumstances. And so in that context, we can get QP, meaning for the pressure, is going to be equal to the equilibrium constant for pressure times Q, and so that will just be equal to products over the reactants here to the exponential of the pressures. Now, the pressure and the concentration constants, equilibrium constants, are going to be different. The way that they're different, if you take a look here, Kp is going to equal Kc, the concentration, because we know that the concentration is just, PV equals nRT. And then if we go P, it's just going to be N over V times RT. Okay, so the difference in this guy is just going to be that RT to the delta N, okay, where N represents the number of moles. So it's going to be the change in number of moles from from your products and your reactants. Does that make sense?
Yeah.
Okay. So now, and I'm going to stress that this is the fundamentals of equilibrium, right? This is going to pretty much apply to equilibrium, general equilibrium in general. When we start talking about acid and bases, that is just a special case of the general form of equilibrium. It just kind of allows us to sit there and make some assumptions to make the equations a little bit easier to solve. Okay, when we're talking specifically about acid and bases. When we're talking about solubility, it's just a special case of equilibrium. And then it just gives us a little more guidance to make the equations a little bit easier to solve. And so I'm going to kind of throw a lot of stuff at you guys today and then on Monday that deals with equilibrium, because we have to go through 3 chapters of equilibrium. But essentially, it's going to be the same thing. So I'm going to show you the hard way, and then I'll show you the specialized way. Okay. So first off, write the equilibrium expression for the following. So if we're doing for concentration, what would be the equilibrium expression?
Would we do like the MA plus NB format?
Yep.
To N?
Okay. So would it be 2N or 2NO? 2.
I'm not sure.
Because we're talking about the concentration, right? So I see what you're asking. You're saying, can I just use? So you're talking about the concentration of this guy, right? For concentration. So then it would be bracket, and then it would be to the second power, right? So it's products over what?
Oh, I was looking at the like MA plus NB arrows XCYD.
Yeah. So yeah, it's that, but now you're doing it for real chemical equations.
Oh.
So you're saying Kc, meaning the equilibrium constant for is going to equal what?
It would be over the N2O4 in brackets.
Okay. So it's going to be NO4 in brackets, and that's going to be to the first power. Okay. So that's it. Okay. What about 2? Now we're talking about pressure, Kp.
Or so the top one you said that's equal to Kc, like, is it just because we're told it's already in equilibrium?
Yeah, you're assuming that it's already in equilibrium, so you're going to make it equal to Kc instead of Q.
Okay.
If we're starting out, if it's at the very beginning or at any point, but it's not at equilibrium, then it would be Q instead of K.
Okay.
Okay, what about Kp for this equation? So what is the difference between Kc and Kp? What does P pertain to?
The partial pressure, right?
Partial pressure. So then we want the partial pressure of each of the gases. Going to do exactly the same thing. So we put P over NO2 squared over P over N2O4 to the first power.
And if it was concentration, that would mean that it's like dissolved in solution, right?
Concentration can be a function of, well, of gases. Gases can have concentration associated with it because it's then you're just looking at volume over, or moles over volume, right? So then you just have P over RT in that case.
Oh, okay. I see. I was just trying to think of like, when
Yeah.
if you had gases, when would you use KC versus KP? But I guess it'll probably just be applied in the question.
Okay. Now what about here? 3. What is going to be the equilibrium constant for that?
Maybe KC. NO2O4 is on top, right?
Yep.
And then 2NO2 is on the bottom. So concentration always has to have the brackets.
Yep.
Okay.
And is the bottom, what is the power? Is it squared or is it cubed or is it the first?
Squared.
That's right. Okay. And what about number 4, even though it says number 3?
Be the KP.
Okay.
And P N2O4 would be on top. Then it would be the PNO2 squared.
Okay, piece of cake.
Hmm.
Okay. Okay, so if we wanted to calculate Q, right? So we want to calculate QC. So at a constant temperature, the following equation has a Kc of 4.18 times 10 to the minus 9. Calculate QC and identify which direction the reaction will be proceeding if the mixture of 0.200 molar hydrogen bromide gas, 0.0100 molar of hydrogen gas, and 0.0100 molar bromine gas. So how would I calculate QC?
If you wanted to write like a base equation first, you would do the concentration of H2 times concentration of Br on top.
Okay. I don't know why it's making my bracket funny.
And then that would all be over concentration of HBr squared.
Okay.
And then we'll just do the plug and play the two n numbers, 0.01 times itself, and 0.2 squared.
My calculator. What they did with it. What do you guys get?
Zero point zero zero 0.0005.
Okay, so which way would we go? Which way would the reaction be favoring or going towards?
So do we look at the mixture concentration?
Nope, you compare the Kc, right?
Oh,
So you look at the Kc, is this Kc bigger or smaller?
smaller.
Definitely smaller.
The
Okay.
reactants.
Okay, so is it going to be going left or right? So you said it favors the reactants. Okay, so it's going to be shifting to the left. Okay,
So like essentially the products are forming reactants faster than reactants are forming products at this moment. Or do I have it backwards?
okay, so you're saying that the
Products
products-
forming reactants faster than vice versa.
yeah, so yeah, in this case, you're saying that, so if it's going to be shifting to the left, that basically means that our reactants, we have more of our reactants than our products being generated. So it's right now we're favoring that reactant component. So we're going to be pushing it to the other direction. Does that make sense?
Yeah.
So it's making more of the reactant, or the reactant's more present?
So right now it's not making, it's the reaction right now favors
The
the
reactant.
reactant, right? Because the reactant is more abundant initially.
Okay.
And so it's going to be driving the equilibrium towards the other direction to try to get favorability of the product.
Okay.
Okay. Okay, and that's a typo. That's was it 0.5?
0.
Okay. Now, at this point, all of our things were gases, or they're going to all be aqueous or something like that. So sometimes we have an issue with the states. Okay, so let's talk about those states. So these are called heterogeneous equilibriums. So in the case of heterogeneous equilibriums, you're not going to take in consideration liquids or solids. The only thing that you're going to be taking in consideration are gases and aqueous solutions. The reason why you don't take liquids and solids into consideration is because liquids and solids, like if we're working with a solid, it's dependent on the surface area of that solid. And so really what's going to cause that reaction to happen is whatever it's surrounded with, that gas or that liquid. Okay, so that's going to be what's going to be affecting your equilibrium. Okay, does that make sense?
Yeah.
Okay,
Equilibrium problems like this, are we
What was
just
that?
doing- for equilibrium problems like this, are we just assuming that like basically there is no limiting reagent? I can't remember that word.
limiting reagent.
Yeah.
Yeah, so in the sense you're assuming that there's no limiting reagent that you have. Well, let me kind of elaborate on it. So usually you're given the concentration, so you know exactly how much you have. And that's going to also affect it, because if you have one product or another product and it's deplenished, that could also drive the reaction as well. Okay, so
Right.
it can drive the equilibrium. It'll shift that. We'll talk about that a little bit later.
Okay.
Okay. So, but that actually is a very good question. Okay, so let's. Okay, so again, you're not going to be basing it on liquids or solids. Okay, so if we're going to write the equilibrium constant for this, the expression for the equilibrium constant, what would be the equilibrium constant in this case? For, let's say the first question says, write the equilibrium expression for Kc for solid diarsenic trioxide reacting with fluorine gas to produce liquid arsenic pentafluoride and oxygen.
Well, first we would have to get the equation.
Okay, so what would be the equation?
I mean, I know diarsenic trioxide would be As2O3.
As2O3.
Why is it called diarsenic trioxide though? Wouldn't that be like an ionic bond? So you wouldn't have to do the di and tri?
No, arsenic is a metalloid, and so it has characteristics of metals and then also of nonmetals. And so in certain circumstances, it's going to act like a nonmetal, so it's going to form covalent bonds. In other cases, it acts like a metal, and it's going to form ionic bonds. In this case, it's a covalent bond.
Oh, okay.
It'd be
Okay.
F plus F2.
That's me.
Yields.
You know, it's an
Um,
equilibrium.
AS. What was penta 5? I don't
So it's
remember.
yeah, F5
5.
and O2 gas.
Yeah.
And that's
Plus
liquid.
O2.
O2 gas.
So fluoride is definitely a gas, and then the arsenic. Oh yeah, solid. It says so.
Okay.
So would you alleviate the solid and the liquid? It would just be the F2O2.
That's correct. So then our Kc is going to be concentration of O2.
Wait, we would have to make this balance first. It's
Oh yeah, thank you. I got carried away.
It's kind of a weird one balance, so I'm trying to figure out how to do it. Do we start with putting X2, the arsenic pentafluoride?
Okay.
So would that be 5 then in front of the fluorine because it's 10 and 10?
Okay.
So we multiply that by 3/2 and then just do 2 times everything, I guess?
You said multiply by 3/2. Okay.
Yeah, the O2 multiplied by 3/2 and then do the whole equation by 2, I guess.
Okay. So then multiply everything by 2 after that. So we'll end up with 3, 6,
10,
10,
2.
and 2. Okay. So then
So it'd be 302 divided by 10 F2.
The 3 would be the power.
okay.
And then it'd be F2 to the 10th power.
Okay. Piece of cake.
So for an equation like this, would we be allowed to leave the 3 halves on the O2 gas just like that and just use that for the power? Or does it have to be like no fraction?
So that's a good question. So I have to think about that. I would normally not use the halves because it always gets me in trouble later on. I have to think about the value that you get out of that because it actually will affect, because in one case you'll have 5, in the other case you'll have 3 halves.
Right.
And so I guess technically it'll be, I think it's going to affect the overall outcome, but I have to think about that. So
Just to be safe, though, we should probably just eliminate fractions.
yeah.
Okay.
Yeah. Okay. So what about write the equilibrium expression for Kp for the equation below?
So wouldn't it just be the Kp equals O2?
The pressure of O2.
Okay.
Right, because the other 2 are solid, so you don't count.
Oh, sorry. Kp would equal PO2. That's correct. Okay. Le Châtelier's principle. So Le Châtelier's principle is basically, it lets us know how the equilibrium is going to shift. Okay. So let's go over some of the rules of Le Châtelier's principle. So it basically tells us which direction that the equilibrium system is going to be going to, which one is favored right now and which one is going to be going. Okay. So because when things are out of whack, let's say we're just putting something into a system, it's not initially in equilibrium. And then when we put it into the system, it's going to shift accordingly to sit there and try to get to equilibrium. Okay. And so the shift is going to be either favoring the reactants or is going to be favoring their product. So because it's trying to get to that point of equilibrium. So one is going to be favored. And so that means that we're going to be shifting towards the other. And so the idea is that you're going to try to figure out when it's going to shift. Okay. So your shift can be a result of concentrations. It could be a result of partial pressures. It could be a result of temperature. And it could be a result of total pressure change. Okay. So we know that the equilibrium is going to shift as a result of concentration changes for aqueous products or reactants. We know that it's going to be change as a result of pressure as well too. Okay, so we want to sit there and determine how it's going to shift in regards to these things that are being added. Okay. Okay, so if we're adding things to the reactant, then it's going to shift to the right. If we're adding things to the product, it's going to shift to the left. Okay. And if we're removing things from the reactant, then it's going to be shifting to the left. And then if we're moving stuff from the reactant, then it's going to shift to the right. Okay. So we have the system. In this system, we have carbon monoxide reacting with that'd be iron 4. Sorry. That's 8. No, iron 6, I believe. 18. 4 times 2. 4 times 2 is 8.
Yeah, that's weird. If it would be 8 divided by 3, so there's charge.
That is a weird compound. It's what? So 8 divided by 3, that is
Dr. Hetty's like, even this one is beyond me.
yeah, I'll have to look at that again. So it could be peroxide. So if it's peroxide, that still wouldn't work. -1. Yeah, that one's beyond me. So I'll have to look that one up myself. Iron something, some type of oxide specialty. So in this case, which way is it going to be shifting if we add carbon monoxide?
Well,
Isn't it dependent on if we're adding to reactant or product?
Because we're making carbon monoxide, the addition of carbon monoxide. We have carbon dioxide as a product, right? So is it going to be dependent? What are we adding to? Are we adding to the reactant or are we adding to the products? If we're adding more, so basically we have our system in equilibrium, and now we're pumping in more carbon monoxide. What's going to happen?
Monoxide is on the reactant side, so it's going to shift to the right.
Okay.
Yeah, I don't know. Yeah.
That's correct.
Okay.
Okay, so we're going to be driving the reaction this way, right? Okay, now we're removing carbon dioxide. So now we're taking this guy out.
Opposite is affected.
So shift to favor reactant, shift left.
Are you sure?
So it's opposite, so it's going to shift.
So you have less of this.
Is it going to go back to the reactant, so left?
Are you sure?
Oh, no.
Gonna want to supplement, right?
It's going to want to supplement. So what is it going to do if it wants to supplement?
Oh, so it's going to end up creating more product. I see.
That's right. It's going to drive it this way. So you're removing it out of the system. And so that means that it's saying, you know, at first it's an equilibrium, and now you're removing this guy. So then it's going to shift the equilibrium towards the product.
Like
So
you
it's gonna
disrupted equilibrium, so it needs to go back.
That's right.
Okay.
It's going to shift right again.
So okay, so hypothetically, if we were to remove like the carbon monoxide, we would still have a shift towards the reactants.
So if you remove the carbon monoxide, then you would have a shift towards the reactant. That's right.
Okay, so any removal is going to shift towards the favored side.
Yeah. So any removal is going to shift towards the side that's being removed. Yes.
Okay.
Okay. What about the addition of Fe3O4 solid?
That's gonna go right.
Is it?
It's not gonna do anything.
It's not going to do anything.
Solid.
That's right. Because remember, the solid isn't going to affect the,
Oh shoot. Okay, yeah.
as long as it's there, it's not going to affect the reaction, right?
So anything other than solid will affect the reaction.
Yes. Well, no,
Or
that isn't
liquid,
true.
right?
Solids or liquids.
Yeah.
Aqueous and gas only.
That's right. Okay. What about the addition of? What about the
So-
addition of CO2?
That one's gonna go left.
Okay. Okay. Questions, concerns, Cash? Crayolas? Okay. Okay, so in the case of pressure, so if we have partial pressures, that's going to result in a shift, okay? So the equilibrium is going to be, shifted with partial pressure changes. So if we get an increase, it's going to, an increase in a reactant, it's going to shift it right or left.
Right?
It's going to shift it right. If we get an increase in a product, is it going to shift it right or left?
Left.
Okay. Okay, so first question here, increase of hydrogen gas, the pressure of hydrogen gas.
So it's shifting right.
Okay, what about an increase in hydrogen iodide?
Left.
Okay. What about a decrease in iodine?
It is that the one where it would shift left still?
That's right, it's a shift left because you're trying to compensate to make up for that loss in pressure. And what about?
So then that one would be right.
Yep.
So it's like a balancing game, right, Dr. Henry?
What was that?
Is it like a balancing game?
Yeah, it is a balancing game. You know, it's kind of like
Nature's balancing game.
what was that?
I said it's nature's balancing game.
That's right. Yeah. Okay. So now temperature. Now, if we think about the temperature of a reaction, okay. So the equilibrium is going to shift as a result of temperature. Because we know one thing, if you increase gases, I mean, if you increase the temperature on a gas system, you're going to increase molecules that are moving, right? So that's one thing to sit there and think about. The other thing is to think about, so when energy is being put into the system, so like say, for instance, we have this equation here. So this guy has a positive value associated with it. So is it going to be endothermic or is it going to be exothermic?
I always forget this. The positive value is like from the perspective of the molecules in the reaction. Right? Like the molecules are absorbing heat. That's why it's positive.
Okay, that's right. So in that case, it's going to be an endothermic reaction, right? Because you have to put heat into it for it to do something. And so an exothermic reaction is going to be a negative value. Okay, that means heat is going to be released. Okay, so the addition of heat to an endothermic reaction will shift the equilibrium to the right. Okay, where removal of heat will shift the equilibrium to the left. Okay, so in other words, if you're putting in extra, you're going to be driving that reaction in the case of an endothermic reaction towards the product. And then if you're removing heat from the system, then you're going to be driving it towards the reactant. Okay. So in the case of an exothermic reaction, if we're adding heat to the system, that's going to do what?
So for the top one, it's adding more heat would favor the product.
So if the reaction is an exothermic reaction, meaning that this has a negative value, if we're adding more heat to the system, it's going to favor, is it going to shift left or right?
If it's exo and you're adding more in it, is it shifting left because it's exothermic?
That's right. It's going to be shifting left, right? So in other words, you're going to be driving the reaction towards the other way, right? Because in that case, it's going to try to compensate. It's saying, I'm making too much heat, so I'm going to push it in the other direction. Okay, so if I'm removing heat in the case of an exothermic reaction, so normally it's like negative whatever, and now you're removing more heat, you're removing that heat from there. What's going to happen in that case?
Other way.
And shift right.
It's going to shift right.
Because you.
Okay. Okay, so this equation here, is it an exothermic or is it an endothermic reaction?
Endo.
Okay, so this guy's an endothermic reaction. So since it's an endothermic reaction, heat's being added to the system, what's going to happen?
It's going to go right.
I'm just trying to think about this like conceptually. Is it like because it requires heat for the reaction to occur, less heat just means the reaction is occurring, like it's just occurring less?
Because this guy requires heat, right? So in other words, you're putting in too much heat. And so that's just going to drive your reaction more to the right. Because it's going to try to compensate to get rid of that heat. The way that it gets rid of the heat is by absorbing more of it.
Oh, okay. I think I understand that one. Okay.
So if the system is being cooled, so then what's going to happen?
So shift to the left.
That's right. Okay. So here, this guy is an exothermic reaction. So since it's an exothermic reaction, that means energy is being released from the system, right? So if I'm adding more heat to this, what's going to happen?
It'll shift to the left.
That is correct. And then if it's being cooled,
The right.
that's right. Okay, so the way what helps me is because I always think of it as heat as a reactant or a product. If I know that it's positive, that means that it's on this side. So I always think of my heat being over here.
The
Right.
negatives and positives always throw me off because I feel like they should be opposite to what they are. I have to remember
Yeah.
like, it's from the perspective of the molecules themselves.
That's
If it's
right.
positive, they're, you know,
Okay, and so then when it's exothermic, it's on this side, right? So I always look at it like this. So I'm adding more of my product, or heat is more of a product, right? More heat is going to drive it in this direction. Okay, so it's going to drive it to the left. And then if I remove heat, then it's going to drive it to the right. So I look at it just as one of the other things that are being added to the system. Okay. Now I'm gonna mess up your head now. Okay. So now we're gonna talk about total pressure. So total pressure is gonna be kind of dependent on your coefficients. Okay. So the equilibrium is gonna basically shift in favor, or so the equilibrium is gonna shift to try to compensate by either. So if you get an increase in total pressure, it's going to push it to the one that has the fewer molecules. If you get a reduction in the total pressure, it's going to push it to the one that has more molecules. So the one who has the most molecules are going to be the winner. I mean, so I should say. In one case, if the pressure increases, it's going to go to the one that has the smallest amount of molecules. And then if you have a decrease in total pressure, it's going to go to the one that has the most molecules, okay, or most particles. Okay, so an increase in total pressure by the addition of helium gas.
so when you say like total molecules, it's like we were counting N2O4, that's 6 molecules, right? Do we count NO2? Do we
No.
include the 2 when we count the total number of molecules, or is it just 3?
Okay, so when we talk about molecules, this has 2 molecules. This guy has 1 molecule.
Yeah, I'm thinking it wrong.
Right. So don't think about atoms. Think about molecules.
I see. Okay.
Yep.
So then the first one would have 2 total molecules, and the second one is 1 molecule.
That's right.
So it would shift towards the second one.
Okay. So it's going to be shifting towards the
Yes.
Okay. Because you're going, so if you're increasing the pressure, you're going to go to the one that has fewest particles. And then if you're decreasing the pressure, you're going to go to the one that has
most. You're still going left.
Okay. So this one will be to the right. And this guy would be to the left. Okay, makes sense?
Mostly.
Okay. So
I think the
basically any
temperature is
gas,
in this one.
any gas can affect it generally. If you're working with gases. Okay. So it doesn't have to be specifically that particular gas. Did you guys notice that?
Yeah.
Oh, so like okay, I see what you're saying.
Yep. Okay. Okay. So the Haber process is an example where they actually used equilibrium for the production of ammonia. And they basically used, I mean, it basically revolutionized agriculture with this process.
Wasn't it first made to make bombs during like World War II or something?
That is correct. Yeah, it was actually initially used to make bombs. Yep. Where did you read that at?
I don't know. I watched just a bunch of like random YouTube videos about like, I don't know. I'm just a nerd. I just like the, it's like nerding channels.
Yeah. Yeah. No,
And I
that is
just learned that
true.
like Haber, he did this make a bomb, and it's just like about the morality of it, and how it ended up being really good for agriculture. But it was at first made for bombs or whatever.
Yep. Yep, it was actually first used to make bombs. And so the beauty of this is that it's basically using air for the generation of ammonia. And it uses Le Châtelier's principle very, very well. And then also we know that the fact that this guy is an exothermic reaction. So let's see. So here's the diagram. Okay, so here you have air being fed into the system. So you know that air is a lot of nitrogen and hydrogen gas, in addition to oxygen and all that. But air is being fed into the system. It actually goes through, it gets warmed up. And as it heats, it feeds up into the column. It goes to this catalyst. And then you start getting the reaction between the nitrogen gas and the hydrogen gas, and you make some ammonia. So we're basically using that heat to sit there and drive that reaction. We have a whole bunch of one product. We're using heat to sit there and drive the reaction, and it's pushing it towards the other direction. So then we have this guy goes through a heat exchange. It gets through here. Here we're basically feeding in cold water, and it's cooling off the ammonia and the unreacted nitrogen, hydrogen gas. Well, the gas is going to remain a gas, I should say, and it's actually using cool recycled ammonia to sit there and cool off the system, not water. So it goes to this condenser, and then it condenses the ammonia. The ammonia is being removed from that system, so you have no or little ammonia that's going through here to this recycle vent, and it goes to that process again. So here it goes that entire process all over again with the ammonia that's being recycled. And so in this case, we're removing the ammonia, so it drives the reaction to make more and more ammonia. Okay, and then we also use temperature as means to sit there and also drive the reaction. Does that make sense? You guys get it? Okay. Questions, concerns, Cash? Okay, so the next thing that we want to talk about is actually how to use the equilibrium constant for calculating values. Okay, and so there's basically 6 steps. First thing that you always want to do is try to identify your constant that's going to be being used. So you want to know if you're going to be using a Kc or a Kp. And if you may end up having to use a combination of both, converting Kc to Kp or converting Kp into Kc. You want to write out the equation quotient using the balanced chemical equation. So you need a balanced chemical equation, and you need to be able to write out the quotient. You're going to use that Q value to determine your starting position. And then we're going to use what we call an ICE table. An ICE table basically is a table that gives us the initial, change, and the equilibrium conditions. Okay, and then I'll show you how to go about that process. And then sometimes to make our lives a little bit easier, what we're going to use is we're going to make the assumption to simplify and check based upon 5% rule. So you're gonna, in some situations, you're going to be able to neglect a number or what you, or that unknown, because it's not gonna affect the system by more than, if it affects it less than 5%, you're gonna ignore it, okay? Or you believe it to affect it by 5%, you're gonna be able to ignore it. Then you're gonna solve the algebraic equation using the quadratic formula. You guys remember the quadratic formula?
Yeah.
So I always have a table because I always forget it. So I have a little,
The program
Well-
calculator to be able to do it.
yeah. So I found a link online that I typically do. So I'll provide you guys with that. So you can plug it in once you get it in the right format. Okay. Okay, so using the following equation, I say use the following equation with an equilibrium constant Kc equals 9.30 times 10 to the minus 8 to calculate the concentration of hydrogen gas at equilibrium if 0.50 moles of hydrogen disulfide gas is placed in a 3.00 liter container. Okay, so what are we gonna do?
Well, I mean, step one is like just identifying we're using concentration instead of pressure.
Okay. So are we gonna use Kc or Kp?
You're finding concentration, so Kc, right?
Okay, so we're gonna have Kc. Kc is gonna equal
It'd be
You
the
want the number or like the equation?
equation. We'll start with the equation because that's gonna be the important part first.
So the concentration of H2 squared. And then times the concentration of S2.
over the
Sorry. It's been a long week. Okay. You guys agree with that?
Mhm.
Mhm.
Okay. So we're gonna make an ice table. Basically, we have the initial, the change, and the equilibrium. Okay, so initial, we're starting off with nothing of this, nothing of this. All of it is hydrogen disulfide, right? And what is the concentration that we're starting off with?
The 0.450.
We would have to put that over 3 though, right? With the molarity.
That's correct. We'd have to put it over 3. So then it'll be 0.15. Molar, which is moles over liter. So molarity equals, or let me say, concentration of H2S is going to equal 0.450 moles over 3 liters. Okay. So what's going to be happening? So right now, who are we favoring? Are we favoring our reactant? And what's going to cause us to go, or are we going to go towards an equilibrium? I should say. Do we have any product?
Yeah, so we'll go
Okay,
towards
So in the
product
beginning,
equilibrium.
we only have the reactant, right? So during the change, what's going to happen?
It's gonna disassociate.
Okay, so it's going to break down. Okay, so and then you're going to get what generated?
The hydrogen and sulfonic acid.
Okay, so when we look at this, right, and we have to take in consideration what's being made and how much is being made. Okay, so what is the ratio between this guy to this guy?
2 to 2.
It's a 2 to 2 ratio, right? Okay, so then we could just say, okay, so we're going to be making X of that. And then what about this guy?
It's 2 to 1.
It's 2 to 1. So then so 1/2 of X, right? Okay, so then that's going to be the change here. So these guys are going to be gaining that. Then this guy is going to be,
So would that one be minus X?
that's right.
So could
Okay.
you also do this? I mean, I have quickly, but you could just do -2x plus X and then just 1x over there.
Yeah, you could also have done it that way. Yeah.
Okay.
So 0.150 molar minus X this guy is just going to be X, and this guy is going to be 1/2 X. Okay, so then we put this guy in for our concentrations. So at equilibrium, it's going to equal X squared times 1/2 X over 0.150 minus X squared. Okay, so in this case, what I would always do is kind of take a look at my K value. Okay, so based upon my K value, I make a decision whether or not that X is going to be a big number or if that X is going to be a relatively small number, right?
So it's going to be small,
So
or it'll be large.
Yeah, because KC is also really small. So
K is really, really small, right?
yeah.
So if we, let's say for instance, if we neglect this guy, right? We're assuming that K is going to have very little value. So that means K being small, that means that your product, your reactant is basically going to be larger, much larger than your product, right? And so
Shouldn't it be reversed? The product is on top and the reactant's on bottom. It's a small one number
I'm
than
sorry.
the bottom.
Thank you.
Related.
My reactant is going to be much larger than my product, right? So that means that my products are going to be really, really tiny in this case, right? So if this is subtracting those products, this value is going to be so small that it's going to be negligible in a sense. Okay, so then I can neglect that X 0.150 molar, and then I square that over this guy is now x cubed 1/2. And then I plug in my value for k, which is 9.30 times 10 to the minus 8. I'm going to finish this guy up here. Okay, so and then we want to take the cube root. So okay, so then I end up with x cubed equals, let's see, 4.18 times 10 to the minus 9. And so then I get x equals 1.61 times 10 to the minus 3.
And it's only positive because it's like an amount, right?
That's right. It's always going to be a positive value. You should never end up with a negative value.
Okay.
Yeah. And you should never end up with more than what you start out with. So those are always like telltale signs.
Right. Yeah, definitely not good if you end up with more than you started.
Yeah. Okay.
So now we check if that's
Yep.
accurate.
Yep. So you plug it in with the real values and see how far off you are. So if it's more than 5% off, then you know that you made a mistake, or that you can't make that assumption. Okay, so you plug it in here and see if your K value, what your K value is. If you're 5% off of that K value, then you know that it's incorrect. And so you can't make that assumption. You got to do it the hard way. Okay. Questions, concerns, Cash? Okay. Or you could, another way of doing it is taking a look at how much different this is. If this guy is more than 5%, the value here is more than 5% of the initial value, then you also know that you also have a problem. Okay.
Okay. Yeah, for this one, I think it'd be super annoying to solve for x long way because it's cubed. So I don't even know if you always use quadratic. But
Can you repeat that, please?
I said for this one, like if we had to solve it the long way, because it's cubed, we wouldn't be able to use quadratic, right?
No, we wouldn't. We'd have to use, you could do it by, I'll show you a way of doing it via Excel.
Okay.
And so you'd have to be able to solve the different roots, but I'll show you a way of doing it via Excel next week.
Okay, yeah.
Yeah.
'Cause I can for sure do it with squared, always use quadratic for that, but the cubed, I don't even know.
Yeah. Okay, questions, concerns, Cash, Crayolas?
It's just so overwhelming. There's so much work.
It's multi-step, yeah. And so if you remember the ice table always leads you in the right path. Okay.
Okay.
Okay, so we're going to stop here and then we'll pick it back up on Monday. And basically, again, on Monday, we're going to go through a lot of different types of equilibriums. So I'm going to kind of shorten the lectures a little bit. They're just going to be segments of each one. So we're not going to do like 50 questions of this type of equilibrium. We're going to probably do like 1 or 2, and then we're going to move to the next type of equilibrium. Okay.
Okay. Dr. Henry, we have the lab tonight, right? For
Yes, you're going to have the lab tonight. I'll be putting it up officially when I get a moment to do it. I just have not had a moment. So
okay.
trying to
Just
play
making
catch up on everything. Yep.
All right. I'll see you then.
Okay, I'll see you guys tonight. You guys have your sugar and everything?
I'm
Yeah.
gonna go buy my fruit.
Okay, good. So you want a key to kind of get started early. You want to puree it if you can. And make sure you have no seeds in it, you know.
Okay.
Oh, wait, what fruit do you use it?
Whatever
use-
fruit you want.
Whatever fruit you want.
Does it say like how much or?
Yeah.
2.5 to 5 pounds.
Yep.
Okay, well, what fruit do you recommend, Dr. Henry? Because I've never made wine before. Just grape?
I think strawberry wine is a great one, and it's pretty
Ooh.
easy to do. You can always go with the classic that never fails. Great. You could do blueberry. Blueberry makes a beautiful wine.
Okay.
You could get fancy and throw a little bit of hibiscus in there. Let's see. You could do peach. We've done peach. We've done watermelon. Done
Oh, wow.
cantaloupe. Done pear. Done apple.
Well, I'll just ask my sister then what she wants to do, I guess. She'll probably want to do strawberry.
Yeah, banana or banana strawberry.
You said to puree it with no seeds. Is that what you said?
Yeah, you want to puree it.
Okay.
So if you have peaches, you want to make sure you cut the seeds out and then
Yeah.
puree it, and you try to get the most ripest ones.
All
So
right.
when you go there, get the ones that they look horrible, you know, and they're.
Well, they have most sugar in them.
That's right.
Okay.
Okay.
And can I do the lab tomorrow?
Yeah. Yep.
Okay.
Yep. You can come in during one of my classes if you want to, or
Okay.
in the morning, you know, when I'm grading. So. Okay.
All right.
Don't look so sad, Cassie. It's okay.
I just have a lot. I have to go to the doctor's right now and everything too. So.
Okay.
What time tomorrow?
I will be available around 9.
Okay. Cool.
Yeah, 9 in the morning. Or you can come during my lab, or I guess tomorrow's office hours. Not bad. Today's Wednesday, right? I don't know what today is.
Today is Wednesday.
Okay, God, this week is flying by.
Somehow COVID has felt like 10 years and also only 1 week at the same time. It's crazy.
Yeah. Yeah. I feel exactly the same way. Certain
Yeah.
things is taking forever, and the other things is just like, oh my God, it's going by way too fast.
Yeah.
Okay, I need to let you go. I have a class that's waiting for me.
All right.
Probably ready to jump ship.
Bye, Dr. Henry.
Okay, I'll see you guys.